The Great Pyramid is the only surviving wonder of the 7 wonders of the ancient world. It is a legendary structure by all standards, and almost everything has already been said about the ingenuity of its construction. It is enough to mention that, to this day, expeditions and studies from various scientific fields are still allocating budgets to research its mysteries. Even more astonishing is that, since 2015, particle physicists themselves have been continuously studying and collecting data on a new secret hidden deep within the pyramid. That alone makes the Great Pyramid, or the Pyramid of Khufu, a must-have topic on our channel. In short, the original height of the Great Pyramid, before some stones were removed, was approximately 150 meters, equivalent to a 50-story skyscraper. Although its current height is around 139 meters, it is still an architectural marvel. Now, imagine a massive skyscraper with only one apartment inside. Sounds suspicious, right? This is not just my opinion. It is what all enthusiasts studying the Great Pyramid believe. To this day, only 3 rooms and a hallway have been discovered inside the pyramid. These rooms have been categorized as follows: a mysterious underground chamber whose purpose remains debated. 2 adjacent rooms near the pyramid center, identified as the King's Chamber and the Queen's Chamber. A large hall near these chambers, considered a passageway. The presence of such limited spaces inside a colossal structure has always raised questions among researchers. Over the years, numerous archaeological missions have attempted to uncover more hidden areas. However, 2 major challenges have always stood in their way: the complex and narrow passages of the pyramid, which make it difficult to use advanced equipment; the risk of drilling or moving the massive stone blocks, as even a minor miscalculation could cause structural collapse. These challenges persisted until particle physicists entered the scene. By using advanced technology and collecting data for nearly 2 years, physicists announced a groundbreaking discovery in 2017, an unknown void hidden deep within the pyramid. However, due to a lack of data, scientists could not definitively classify this space. Theories suggest it could be a passageway, a hall, a structure, or even multiple parallel structures. Research and data collection are still ongoing as we speak. For scientists, this is being hailed as the discovery of the century. But what truly matters to us on this channel is that this discovery would have been impossible without advancements in particle physics. So let's dive deeper into this finding, and more importantly, understand how particle physics played a crucial role in uncovering it. Make sure to like and share so we can continue bringing you amazing content. Welcome to a new episode of Unveil the Universe. Of course, we will discuss this important discovery in more detail, but first, we need to review some key physics concepts. These concepts will help us understand the role of nuclear physics in this breakthrough. The first of these concepts is cosmic rays. Cosmic rays are high-energy particles that reach us from space. They travel throughout the universe and visit every corner of it. Essentially, they are atoms that have disintegrated, releasing their components. Most of the cosmic rays that reach Earth originate from the Sun. However, other sources, including distant stars, also contribute to these rays. All cosmic rays that reach us possess extremely high energy, traveling at speeds close to the speed of light. As they approach Earth, the planet's magnetic field deflects most of them. The remaining rays that make it through are then largely absorbed by the Earth's atmosphere, leaving only a minimal amount to reach the surface. Although this residual radiation is relatively small, it is still measured in trillions of particles. Every single day, trillions of cosmic particles bombard our planet. Scientists had noticed this phenomenon as early as the 18th century. At the time, it was widely believed that air was an insulator and did not conduct electricity. However, experimental results kept showing unusual phenomena, indicating the presence of charged particles in the air. At certain moments, the air behaved as a conductor, while at others, it was an insulator. The source of these charged particles remained a mystery until Austrian physicist Victor Hess solved it in 1912. To prove that these particles were coming from space, Victor Hess conducted a simple yet famous experiment known as the Hess balloon experiment. He launched balloons to higher altitudes in the atmosphere and measured radiation levels before takeoff and after landing. He found that the higher the balloon ascended, the more radiation it detected. This led him to conclude that the particles originated from space. For this discovery, Victor Hess was awarded the Nobel Prize as the discoverer of cosmic rays. Ever since Hess's discovery, physicists and chemists have been fascinated by cosmic rays. To them, these particles are like cosmic visitors from across the universe. By studying their behavior and the conditions they experienced along their journey, scientists can learn a great deal about space. More importantly, because cosmic rays are simply particles released from atoms, they provide key insights into the physical and chemical composition of the universe. At the time of Hess's discovery, particle physics as a field did not even exist. The only known subatomic particles were protons, neutrons, and electrons. But with the help of cosmic rays, scientists quickly started identifying new fundamental particles. It all began in 1933 with the discovery of the positron, the antimatter counterpart of the electron. Shortly afterward, new particles were being discovered at an accelerated rate. This revolution led to the foundation of modern particle physics. Yet, the discoveries did not stop there. Scientists quickly realized that cosmic rays, despite their fascinating properties, could be harmful to humans and the environment. This led them to hypothesize that something must be protecting Earth from these rays. Through further studies, scientists discovered the Earth's magnetic field in 1958 and learned more about the atmosphere's role in shielding us from cosmic radiation. It was found that Earth's magnetic and atmospheric shields block 99.9% of harmful radiation from space. The remaining small fraction that does penetrate is within safe limits for humans. Additionally, the discovery of cosmic rays led to the development of particle accelerators, the most famous being the Large Hadron Collider, LHC, at CERN. This connection arises from the fact that cosmic ray interactions mimic the high-energy collisions occurring in space, such as supernova explosions and even galaxy collisions. The study of cosmic rays has unlocked countless advancements in physics, helping scientists understand the universe in ways never before possible. As mentioned earlier, the discovery of the positron was only the beginning. Soon after, more particles were found, including the muon, which played a crucial role in the historic discovery inside the pyramid. The muon is one of the fundamental subatomic particles, meaning it is not composed of smaller particles, just like quarks and electrons. The muon is closely related to the electron. It is a negatively charged particle with half-integer spin, just like the electron. Both particles belong to the same family, called leptons. However, the muon is 207 times heavier than the electron, making it a significantly more massive particle. Additionally, the muon has a relatively long lifespan, ranking second only to the neutron in terms of stability. Muons have a remarkably long lifespan that other particles can only envy. Their existence lasts for more than 2 millionths of a second, exactly 2.2 microseconds. A microsecond is 1 millionth of a second. Like other particles, the muon has an antiparticle, the antimuon, which carries a positive charge. One of the most important characteristics of muons is that they are among the first to be affected during collisions. This is precisely why they were among the earliest particles discovered in cosmic rays. Muons leave atoms and travel at nearly the speed of light as radiation. This radiation loses most of its muons upon colliding with the magnetic field and atmosphere. Despite this, the remaining muons still reach every centimeter of Earth's surface. In fact, they penetrate the Earth's crust and dissipate into the depths, where their long journey through the universe finally comes to an end. At this point, someone paying close attention might ask, how can you say they come from the depths of the universe? Didn't you just say that muons exist for around 2 millionths of a second? Even if we assume they last for a full second, a muon would only travel 300,000 kilometers in its entire lifetime, assuming it moves at exactly the speed of light. So how could muons from the sun reach us when the sun is over 8 light minutes away? The answer, my friend, lies in just one phrase: time dilation or time expansion. But in short, the faster something moves, the farther it can travel within a shorter time frame. High velocity not only covers great distances, but also slows down time itself. If an object were to travel at the speed of light, time would stop completely, making its duration practically negligible. When applying this concept to muons, which move at nearly the speed of light, even 2 millionths of a second can translate into distances spanning millions or even billions of light years. The third concept we need to cover quickly is radiographic imaging. Radiation-based imaging involves various types of radiation, the most well-known being X-rays, also called Roentgen rays, widely used in medical fields. One specific type of radiation-based imaging relies on muon detection, known as muon tomography. Simply put, muons can measure the thickness of materials they pass through. Using muon detectors, scientists can count the number of muons passing through a given area. Areas with high density, such as thick walls or barriers, allow fewer muons to pass through. Meanwhile, low density or empty areas allow a greater number of muons to pass. By analyzing muon counts, scientists can determine whether a space is empty or solid. This technique is used to study the internal structures of many things, including mountains and volcanoes. By compiling all collected data, scientists can generate detailed 3D images of large structures' interiors. This is exactly the method that was applied to Khufu's pyramid, leading to the recent discovery. If we add a few key details about this discovery, here's what we find. The mysterious void inside the Great Pyramid measures approximately 9 meters in length and 2 meters in width. Despite being a relatively small space within the massive pyramid, it took 2 full years to collect sufficient data. The muon detectors were first placed inside the pyramid in December 2015 by a multidisciplinary team led by Japanese physicist Kunihiro Morishima. After Morishima's initial findings, 2 additional teams conducted independent reviews and measurements. The KEK Particle Physics Research Group, Japan. The French Atomic Energy Commission, CEA. Both teams confirmed Morishima's discovery in July 2017. However, the strange part is that none of the 3 teams, or any archaeologists, could explain the void's purpose. They couldn't even speculate on whether it might be part of a larger network of corridors. At a press conference, Kunihiro Morishima stated, "All we know is that this space exists. It is truly fascinating and justified the long months of data collection." He also emphasized that they had no plans to excavate, but would continue their research using the latest muon detection technology as it evolves. What do you think? Does anyone have a theory about why this corridor exists? Do you think this will be the last discovery inside the Great Pyramid? Or could it be just the beginning of a complex network of hidden chambers? I'll be waiting to see your answers in the comments, and I'll see you soon in another new and informative video.